Continuing on with chapter 5, we want to get into talking about what are called state functions. When we are looking at measuring the properties of systems, each of those properties can be called a function, right? There's some sort of process that corresponds to determining the value of that property. And all of these different functions can be classified as either state functions or path functions. And so state functions are one that depend only on the state of the system. And path functions depend on the path taken for the system to reach a specific state. So when I say state, what I mean is like the condition, right? All the condition that your system is in, where your system could be a piece of material, some sort of chemical reaction, some sort of solution, solid, gas, anything like that. The state, all of the properties of that sample of matter. And so a state function only depends on basically what your system looks like, right? What it looks like right now. State implies kind of like one snapshot. What does it look like right now? Whereas path functions, and we start to talk about path, that's where we're talking about like the journey, what got us to that point. So path functions always describe the change. So how something changes. In the context of the thermodynamic chemistry we've already talked about, enthalpy, you could imagine you have some sort of initial system with a certain enthalpy, and it changes and becomes a new state that has a new enthalpy. The change in enthalpy only depends on the endpoints. It has a delta. We use deltas to describe state functions because all you care about is the change between the two endpoints. Heat is a path function. So heat describes the actual change. How have you actually changed the enthalpy? How much heat has flowed in, how much has flowed out, right? Heat is inherently describing the journey. Enthalpy is describing the endpoints, the start and the end. So imagine you're driving from Baytown to Huntsville. Which of the following aspects of the drive are state functions and which are path functions? So we're going to go visit our Lee College colleagues up in Huntsville. And we're going to drive there, and we're going to want to think there's some ways we can characterize that. So we could first think about, well, how does our location, right? How does our location change as we move, as we do that drive? And so when we think about, is that going to be a state function or is it a path function? And really how we can distinguish those is, does location describe the journey or does it just depend on the endpoints? And so location changes as a state function. Right? If I start in Baytown and I drive to Huntsville, the change in my location from the beginning to the end will always be the same. I may have driven via San Antonio to get to Huntsville. I may not have gone directly there or taken the most direct route, but my location will always change in the same way if I start and end at the same point. For distance traveled, that then describes the journey itself. So that's going to be a path function. Now it matters how you went about going between those endpoints. But if all you care about is how does my location change, you don't actually care about how you got there. Elevation, that's also going to be a state function. There's an elevation in Baytown, there's an elevation in Huntsville. It doesn't matter if you take a road, you go to Big Bend and do some mountain climbing on your way there and have get up really high, or if you just go directly there. Your elevation, relative elevation changes only depend on where you start and end. But say you go through the mountains, your gasoline consumed is going to therefore vary. So that would be a path function. So when we're looking at state functions, we really only care about the beginning and the end. So all properties that we can directly measure are state functions because they depend on us measuring the properties of a state. What is the temperature right now? What is the volume right now? What is the pressure right now? There are state functions that we can't directly measure. Enthalpy, energy are state functions. But these are still things, whenever we see deltas, that always means it's a state function, that we're looking at change, because if you're looking at a change, you can characterize two different states, the initial and the final. There are really two important path functions. They're heat and work. And if you remember, we talked about that those were the ways in which heat transfers, or energy transfers, sorry. And so these path functions are always describing a change, whereas the state functions only depend on the endpoints. So enthalpy is a state function. And this has a lot of applicability. It's really going to affect how we can determine different enthalpy changes for different things. Because if we want to think about a change in enthalpy, all that matters is the endpoints. If you start with a certain set of chemicals and you do a chemical reaction and make a different set of chemicals, those are two endpoints. And the enthalpy change only depends on the starting point and the ending point. It doesn't matter how many steps you take to get there. Are you efficient? Do you only do one chemical reaction? Do you do multiple chemical reactions? It doesn't matter as long as you start and end at the same point. So for example, the enthalpy change, if say you're looking at carbon and oxygen reacting to make carbon dioxide, you could think about that as just one step. They react and become carbon dioxide, or they react, basically you make some carbon monoxide, that reacts again and makes carbon dioxide. So you can think about this as it small changes to the chemicals, or is it overall big changes? But because enthalpy is a state function, the overall change in enthalpy is guaranteed to be the same independent of the path that you take, because the endpoints are the same. When the endpoints are just carbon and oxygen and just carbon dioxide. So we're going to use this in a couple different settings in this set of videos, where we talk about ways that we can calculate delta H's for different reactions based off things we know about other related reactions.